Hello everyone, and welcome to the third video walkthrough for fall 2016. In this video we will be modeling what happens to the body tubes of different materials under the same loading. For our purposes, this will be a tutorial of how to use different materials in the static structural simulation, while in reality this would be a good start for choosing different materials for the rocket body tube. Let's take a quick look at the problem statement. We want to determine which rocket body tube deforms the least under a uniform axial loading. Each tube has an outer diameter of 155 millimeters, an inner diameter of 145 millimeters, and 500 millimeters in length. So the same dimensions. The first is a tube made of carbon fiber, the second is made of fiberglass, and the third is made of Kevlar. These are three materials our structure subteam might use to make the body tube of the rocket. So now that that's done, I'll start a Workbench window. And once that's open, we'll drag a static structural into the workspace. So the special part of this video is we'll be specifying different materials, and where we do that from, at least in the static structural, is in engineering data. And that's the very first cell that you get. So I'll maximize the window, and we'll double click on engineering data to open the tab. You'll get a list of materials that you can use in your simulations. By default, the list is only one member long, and that's structural steel. So we want to add three new materials of our own. So we'll click in the box that formerly said click here to add a new material, and we'll type in carbon fiber, because that's the first body tube that we want to test. We'll click below it and add fiberglass. And we'll click below that and add Kevlar. Now that we've typed in all the names, we need to add properties to these materials. All the properties that apply to solids anyway are found under the toolbox on the left-hand side. You may have to expand some of these to get the full range of properties. To add a property to the material, you click on it and drag it into the box with your material name. We'll add isotropic elasticity to each material, and we'll also add compressive yield strength to each material. Now that the properties are added, we'll need to input some values for the actual. We'll do that first for carbon fiber. For simplicity's sake, I'm just going to input it from another Workbench window I already have open. So first we'll select isotropic elasticity. We'll change the units of Young's modulus to megapascals. And we'll type in 1.25 E5. That's 1.25 times 10 to the 5th megapascals. We'll type in 0.1 for Poisson's ratio. We'll change the yields of the units of compressive yield strength to megapascals. We'll type in 800 for those. These are the exact values that you want to be typing in as I'm saying this. Now that we specified isotropic elasticity and compressive yield strength, we'll move on to the next material. We'll select fiberglass. Once again, we'll change the units of Young's modulus to megapascals, and we'll type in 30,000. Poisson's ratio for this material is 0.21, and we don't need to specify a temperature because for our simulations, Young's modulus and Poisson's ratio aren't going to vary a lot with temperature, so we can neglect those changes. Now, compressive yield strength, will change the units to megapascals once again, and we'll type in 750. Now, for Kevlar, we will type in 70,500 for megapascals for Young's modulus, and we'll type in 0.31 for Poisson's ratio. Compressive yield strength, we will type in as 715 megapascals. Okay, A good rule of thumb is to add the properties relevant to what you'll be testing in your simulation. For example, if you have a thermal condition, you'll want a coefficient of thermal expansion data for all your other properties at different temperatures. At the very least, for static structural simulations, you'll want to specify Young's modulus and Poisson's ratio. If you don't know what those are by now, you can look them up on Wikipedia. Now we're ready for the next step, so we'll go to geometry. To do that, just go back to the project and double-click the geometry cell to launch. Our first step in geometry is to change the units to millimeters because the problem statement is in millimeters. The tubes are cylindrical with an outer diameter and an inner diameter, which is given in the problem. 155 millimeters for our outer diameter, 145 for our inner diameter, and 500 millimeters long. Just a quick reminder before we start sketching. Since we're going to be simulating 3 body tubes, we'll want to draw 3 cross sections in a sketch. So to do that, select your favorite plane and insert a sketch. A good idea is to turn to face the plane that you're sketching on, and I'm going to be zooming out a little bit. We want the scale to be around 200 millimeters because our side lengths for the circle, well, excuse me, circles don't have sides. Our diameters for the circle will be about 155. So we'll get started drawing some circles. Remember, you don't have to be exact because you can dimension them later. And to do that, you can use the general or diameter. This one's 145 millimeters. The outer one will be 155 millimeters. And now we want to draw 2 more cross sections exactly like that. And you can do that without redimensioning the other cross sections. And how you do that is you click away from the first circle so they don't overlap. You click to place the center, and you slowly move out until you see a little R appear. See, there we go, there's our little R. So that means once you click, while the R appears, that is, it will dimension the diameter of this circle to be the diameter of this circle. So you won't have to dimension it again. Another R will show up for the outer circle. So this cross-section is now precisely the same as that cross-section, apart from where it's located, of course. So we'll do this a third time. We'll wait for the little r, or for the first r, and we'll get our second r there. Now we have 3 identical cross-sections. Now that we have those, we need to extrude the sketch. So we'll select the sketch, click Extrude, click Apply, type in 500 in the depth box, hit Enter, then hit F5 to generate, or you could press Generate. Now that we've admired our work a little, we're done with geometry. So I'll see you in Model. Alright, the first thing that we'll do in Model this time around, as opposed to meshing it, is we'll specify the materials. You can do this by expanding the Geometry window and clicking on each solid. Under the Details section, there's a material assignment. You'll want to change the first one to carbon fiber, the second one to fiberglass, and the third one to Kevlar. I like to maintain the order based on their ordering in the table, or the tree here, because I'll probably be zooming around and doing all this crazy stuff, and I'll forget which one is which just by looking there. It's easier to do it by the table. Tree, sorry. Alright, next up is to mesh the bodies. There's not a whole lot involved in meshing these bodies. You guys can just go ahead and generate the mesh, but my version of ANSYS has some problem size limits, so I'll need to insert some sizings. So I'm going to go ahead and do those. You don't need to follow along, but you can watch if you want to. Fun fact, when you're doing edge sizing like that, you always want to specify number of divisions. Okay, now that I'm done with my mesh, we'll link up again and you can follow my lead for the setup. First, we'll want to insert a fixed support, and you can do this at the bottom. You'll want to control click each of the 3 faces on one side and click apply. So that means all 3 of those are fixed supports. You can specify them as one fixed support. It doesn't really change anything. But you do need to insert 3 separate forces. We'll specify each one of them as 2,000 newtons. And we'll change the direction so that they're pointing towards the fixed support. Click apply after you change the direction. Okay, now that our forces are applied, all we need to do is insert solution tools. We'll do equivalent stress and strain. Now that we have all those in there, our materials are specified, our mesh is done, our fixed support is present, and our forces are on the opposite sides of the fixed support. So we're good to go ahead and solve. You always want to check to see if everything is done before you solve. Otherwise, your solution might not be, well, realistic for one. It might not be what you want it to be either. Okay, after that's done, let's check the strain first. As you can see, the strain is different for each material, even though this is a different scale. This would be the true scale, and this would be undeformed. There's basically no change. Like it might have lengthened by 1 pixel. And that's not very much, even on a 4K screen. So let's go back to the auto scale to observe the deformation. Notice which one of the tubes deformed the least. If you check the scale, the least deformation will be on the blue tube. Now that you're done observing the strain, let's switch to stress. Notice that the stress is about the same in each of the tubes, because stress is defined as force divided by the cross-sectional area. The cross-sectional area doesn't change a lot with each amount of force applied, so there are only minor changes at the bottom where the fixed support is. Stress is pretty much the same, and strain is very different. And this is because of the material properties, specifically Young's modulus. This is an important result for our body tube experiment. Now we're basically done with. In the next video, our geometry will be a little more complicated, and I might be using SOLIDWORKS to create it instead of Design Modeler. Until then, good luck on all your midterms and keep on simulating.